So Jordan, there's a question that has really caught my attention. Is there a link between climate change and earthquakes?
Extreme weather, yes, but I've never thought about the effects under our feet.
Neither had I, but then I saw there were some scientists looking at this emerging link between the two.
Is this climate earthquake double whammy the new top of my nightmare list, or is it actually more complicated?
Well, that's what I want to find out.
From the BBC World Service, this is The Climate Question. I'm Jordan Dunbar.
And I'm Greya Jackson.
Well, joining us to talk about this from the Swiss Alps is Dr. Verena Simon. She's a seismologist at the Swiss Seismology Service in Zurich. Hi, Verena.
Hello. Thank you for having me.
Well, it's great to have you here. And across the Atlantic in the US, an earth scientist at Colorado State University, Associate Professor Sean Gallen, welcome.
Thank you for having me.
Can we just start with something really simple? What actually causes an earthquake? Verena?
So the earthquake's outer shell is made of large pieces that are called tectonic plates and that are constantly moving at very, very low speeds. And when these plates move and they push against each other, then stress can build up in the rock over time. And now you must imagine that a rock is not just like a solid block. It contains a lot of cracks and fractures, and we call these faults. And at some point, the stress along these faults can become too much for the friction, like to hold the rock together, and then it suddenly kind of slips. And this sudden slip is the earthquake. And the earthquake then releases its energy through waves that first travel through the ground, and then they can reach the surface, and then you would feel the shaking.
So if you've got these tectonic plates and they're pushing against each other, causing this tension, why are some slippier than others? Why are fault lines more active and you get more earthquakes than other places?
Some faults are just more active because they sit on places where the Earth's forces are pushing, pulling, and sliding more strongly, like, for example, on plate boundaries. But then there are other faults that have rock conditions that make it just easier for them to slip again and again. And then there are maybe other faults that are very quiet for a long time because they are more locked until enough stress builds up until they can crack.
Right.
So it really depends on how much stress is being applied and how easy a particular fault can move. There are also, of course, other influences that might not everybody think of, like external influences. A fault can sit also quiet for a very long time, very close to its actual breaking point, but then something from the outside gives its final push that it can slide. And this can be like water pressure building up in the underground, or some loading changes, or even tidal forces. So this push does not need to be large, but many faults are actually close to this critical failure that small changes in conditions can be enough to make them slip.
That's really interesting, because I always thought of earthquakes as sort of solely happening underground, right? I didn't really realise that things above the ground could influence what happens beneath the ground. Is that where the climate connection comes in, Sean?
Exactly. Is these small changes that can happen due to processes at the Earth's surface, which could be related to hydrology or water circulation, or could be due to changes in surface loads. So the removal of ice or the evaporation of water can significantly affect the local stress field on a fault. So if it's at sort of a threshold of the stress, then when you get these small changes, you can trigger an earthquake.
Right, and because climate change is changing lots of things on the surface, like more water in some areas, glacial ice melt, you're kind of changing these surface level factors that then have an impact on the fact of whether this fault can slip or not.
Exactly. It's this slow, steady buildup of stress or strain in the Earth's crust that allows these faults to get to this critical point or this threshold point. And then climate change modulates these changing conditions and can affect the properties on the fault in terms of water circulation or the stress in terms of changes in loads.
When we say loads and surface loads, so we talk about weight pushing down on
More or
it?
less, yeah, exactly. So exactly. So the it changes the weight on the overlying fault that's there. Exactly.
Sort of like clamping it down almost. So what you're saying is actually climate change isn't the cause of earthquakes, but it might be influencing them in some way.
Exactly. It's sort of, if the faults are near this threshold condition, climate change basically is going to modulate when you might have an earthquake and push it closer to having an earthquake, or could even potentially make it so that it's less likely to have an earthquake, depending on what the change is like.
Verena, I want to come to your new research. You've been out in the field in the Alps. Describe to me the area that we're talking about. What does it look like?
So we're talking about the area of the Mont Blanc. This lies at the border between France, Italy, and Switzerland, and is kind of the heart of the Alps because it hosts the highest peak of Western Europe, the Mont Blanc. But it's also one of the places on Earth where climate change is very visible because temperatures at high altitudes have been rising faster than in the lowlands. On Swiss glaciers, for example, we have lost already like 40% of their masses since 2000. And the glacier Mer de Glace, which is in the Mont Blanc Massif, which is the largest glacier of France, this one has retreated about 1 kilometer just in the last 35 years. So it's not just about the ice that goes away. Also, permafrost is melting, which leads then to more rockfalls and landslides in the regions, especially if you have mountainous regions like we have it here, with steep rock walls that can break down easier.
So I know that your research started looking at the frequency of seismic events in the noughties onwards, but something happened in 2015 where you saw a huge uptick in the number of events. Can you just tell us what happened and why that was the case?
There was a sharp increase in the temperatures at high altitudes in 2015. But on top of that, other researchers also documented an exceptional number of rock falls in the Mont Blanc area that year that is linked to permafrost melting due to this temperature increase. So these rock falls are not just a hazard on the surface, they physically can open new cracks in the rock. The same thing would happen when permafrost melts, because permafrost would act like a seal in a fractured rock that keeps the cracks frozen and closed. But when it melts, those cracks can open up. And with these more rockfalls and permafrost degradation, there are suddenly new pathways for meltwater to reach deeper into the mountain than before. And this is kind of the link to the earthquakes we are studying.
So were you seeing more earthquakes then in that time period with the high temperatures?
Yes. So just to put it in a bigger picture, we have not analyzed only the earthquakes that started in 2015. We actually analyzed the seismicity in the area since 2006. So since we had a continuous recording from a station there. But before 2015, we only recorded a few hundred earthquakes over 9 years with no particular pattern. But since 2015, this earthquake activity increased sharply, and it follows like a seasonal cycle. So it always was rising every autumn and then gradually declining again in early spring.
So Verena, you're describing hotter days, more melt from the ice and the glaciers and that permeating the ground. Why would that cause more earthquakes, though?
So as I said already before, these hotter days mean also that we have more permafrost melting and maybe more rockfalls happening in the area. So this opens new cracks in the rock where meltwater can flow then now deeper into the mountain than it could before. Now the question how this can trigger earthquakes at depth, the water does actually not really need to physically travel all the way down to the depth of the earthquake at around the deepest which we recorded here were around 7 kilometers. You need to imagine it that way, that the rock at depth is already saturated with water in its fractures, and when new meltwater pushes in at the top, the pressure transmits downward through this existing water much faster than the water itself moves. And this increased pressure reduces again the friction that holds the faults in place. And so if two rock surfaces are pressed together, they hold, but when the pressurized water gets in between them, they slip more easily, and then the earthquake can happen.
I see, I see. So hotter days, more meltwater, and also the permafrost and the rock falls are creating more cracks in the rock, which means the water can enter the ground more easily, which is changing the pressure within those subsurface faults, which is causing the plates to slip more easily, and therefore you get a higher frequency of earthquakes. Have I understood you right?
Exactly.
Nice. My question is, Verena, I have not thought of Switzerland as being a very earthquake area or heard about, loads of earthquakes in the Alps. How strong are these tremors?
For the full data sets we looked at, the largest earthquakes we recorded was a magnitude of 3.1.
Now, what is that? I don't know what that means.
So you can imagine it that way, that I would say a magnitude 3 earthquake is something you might feel when you're close by. Maybe if you're moving or sitting on your bike, then you would not feel it because it's just too much other things shaking maybe around you. But it's definitely nothing damaging, so there won't be any houses broken or injuries or whatever.
So Sean, what did you've read about this paper? What did you think of the results?
I think it's really exciting. I think it's some of the more conclusive evidence that I've seen regarding links between changes in climate and earthquake activity. So it's something that's really exciting to me. The other part of it that I really enjoyed about the paper is this clear link between the changes in hydrology in the system and how the water percolates down, and then how effectively these pressure waves end up hypothetically affecting the frictional properties on the fault due to increases in the water pressure. And so it's not only that the empirical link between climate change and earthquake activity is there, it's that there's a really clear and convincing mechanism that's driving it that I found really compelling, and I was very excited about the study.
Verena, I'll be honest, I don't want any more earthquakes anywhere. I know you both study them, but it's quite scary to me. Is this just specific to the Alps, or can we apply this other research to different regions around the world?
In principle, you could apply it to other regions around the world, but there needs to be met certain conditions, because you need faults that are already under stress and close to the breaking point, which is actually common in many parts of the world. And then you also need like a source of water, in our case, like snow or glacier melt, or sometimes it can even be like heavy rainfall. And then you need also these cracks and fractures in the rock that would allow that the water can penetrate actually deeper into the underground. So, for example, the Himalayas would be maybe an obvious case, with enormous glaciers very rapidly melting. And the mountain belt there lies above one of the most dangerous fault systems of the world, with hundreds of millions of people living nearby, but also other areas, more Arctic areas, Alaska, Iceland, Scandinavia, they're all potential candidates for this.
It's absolutely fascinating. And I said before when we started recording that I didn't really realise there was any link at all. So it's really interesting to hear you describe the research. Sean, are there other ways in which climate change could be influencing or impacting the frequency of earthquakes?
Yeah, so beyond these hydrologic changes that can then affect the fluid pressure along the fault, there's other ways that changes in at the Earth's surface can affect stress fields locally around faults that are near their tipping point or triggering point for earthquakes. And one of the most common ways that this happens is through changes in the distribution of water at the Earth's surface. So this would be not just liquid water, but ice in terms of glaciers. And so if you change the amount of water that you have at the Earth's surface, this changes the weight on the overlying fault, and then this will affect the stress field.
Right. Okay. So glaciers melting, we know we've seen that as a result of climate change. But I'm also thinking the opposite might be true. Say a big lake, if it evaporates in a drought, what effect might that have?
It's a similar effect. So there's some recent studies from the Tibetan Plateau that show the evaporation of some large lakes that are near faults in that area, likely triggered earthquakes on faults that were favorably oriented with respect to those lakes. And then they also show that some of the faults that aren't favorably oriented may have been pushed closer together and were less likely to slip after the lakes evaporated. It's also been shown in certain cases that changes in the amount of groundwater can affect fault activity. And this can be due to climate change, but also due to human use of the groundwater and depleting those groundwater resources over time.
Sean, are we just talking about earthquakes here, or are we talking about a cascade of effects that can happen as a result of an earthquake, like a landslide or a rockfall, for instance?
Yes, certainly. So it's not just isolated to the single hazard. If you wanted to play this out, where you have a climate change that affects the fault, makes it go over this tipping point or threshold, and you have a large earthquake that's big enough to shake the ground surface, you can generate catastrophic landsliding due to that. So that's one effect, and then beyond that, then that changes that change affects the amount of sediment that's moving through the river system in the aftermath of the earthquake, and that can actually impact the shape of the river channels and affect flooding hazards. So there's sort of this myriad of effects that can occur due to one triggering event. The other thing that can happen too is that when we have earthquakes, it'll change the stress distribution around where that fault was that had an earthquake. And this can push faults, adjacent faults, nearby faults, closer to failure or further from failure. So you can actually initiate an earthquake sequence in some cases where earthquake on one fault changes the stress on another, and then it might push that fault to failure and have another earthquake in quick succession afterwards. And quick succession, I mean years to decades after the initial earthquake.
You've also looked into the very distant past to understand what's happened in Colorado, where there were once lots and lots and lots of glaciers, which sort of clamped down the crust. Can you just tell us a bit about your research and how that's all pulled together with earthquakes as well?
Yeah, so I did a study with a master's student of mine named Cece Hurtado a few years ago, and we looked at the Sangre de Cristo Mountains, which are at the northern part of the Rio Grande Rift, which is a rift or an area where the continent is pulling apart that extends from Colorado all the way down south through Mexico. And it's linked by a series of faults in that area. And in the Sangre de Cristo Mountains, it was glaciated during the last ice age, during the last glacial maximum. And those glaciers now are completely gone. And we know that the fault has been active over geologic time, and there are markers that we can look at along the front of the mountain range where the fault is located that allow us to measure the amount that the fault has slipped over different amounts of time. And what we were able to show in that study is that the melting of the glaciers perturbed the stress field on the fault to make it more favorable for the fault to slip. Basically, what it did was the Earth's crust rebounded when the glaciers melted, and it pulled the faults apart a little bit, and it unclamped them, making it so that any strain that had accumulated during the glacier interval was much more likely to be released when the glaciers melted. And then what we were able to show is that the amount that the crust would have rebounded or uplifted due to the removal of the weight of the glaciers matched the amount of slip that we saw on the fault that we were able to measure in the post-glacial period. And the last little bit of evidence that we were able to show is that the rates of slip on the fault in the post-glacial period after the melting were about 10 times higher than they were before before the glaciers melted. So it suggests that there's an acceleration in the rate of motion in the post-glacial period. And so all of this is basically, it's not conclusive evidence, but it's a bunch of pieces of evidence that suggest that the melting of the glaciers affects the stress field and then can cause the crust to rebound in a way that is mimicked by the slip patterns that we see on the fault. So it does seem to implicate melting of glaciers as a mechanism for driving slip.
Right. So we're talking about increasing frequency of earthquake, but not necessarily more intense or worse or higher magnitude earthquakes, both in the glacial record, but also what we're seeing in the Alps. And it's quite, by the sounds of it, region specific. In some areas, it might have the opposite effect.
Exactly. So I think the key thing is that the earthquakes are likely to happen regardless. And what's happening is that the changes in climate that are affecting these loads or affecting the water that's circulating through the system are affecting when the earthquakes are occurring. It does appear to be region specific. So it depends on those various different ingredients that we have. Do you have a fault that is near a threshold? Is the change pulling the fault apart, making it more favorable to slip, or is it pushing it together, making it less favorable to slip? And so these are the different types of conditions that you need to consider when you're thinking about the influence of climate change on fault activity and earthquakes.
Well, Verena, how worried should I be about these climate influences then on earthquakes?
On the Richter scale, Jordan on 10 on the Richter scale is like nail biting, can't get out of bed, and number 1 is, every day.
For the moment, not too scared for this region, definitely, because we have seen for the last years that we didn't record an earthquake that was larger than magnitude 3.1. And actually, the fault that produces a 3.1 earthquake is only a few kilometers long. So to produce a much bigger earthquake of that size would also need a bigger fault. So like the fault size is kind of a natural limit of how big earthquakes can get. There are larger fault systems in this area, in the Mont Blanc region. There has been historical records that include a magnitude 5.3 earthquakes in Chamonix in France in 1905, something like this. But whether this increased meltwater is also affecting these larger faults is something we cannot answer yet, but what we need to investigate. But I would say for now, the earthquakes are definitely not a threat, but the direction is clear and we should keep on monitoring that.
Cautiously concerned.
Cautiously concerned. Do you agree, Sean?
I agree. I think that one of the things I'd say is I think we don't expect to see like a big global increase in earthquake activity necessarily from climate change, but locally this can, and regionally we might expect to see these changes, which will affect seismic hazard in the area. But what I would say is that at this moment we don't think, but we don't necessarily know if it can affect the large magnitude of the earthquakes that occur. My hunch is that no, it's not going to affect whether or not the earthquakes will be bigger or smaller necessarily, but it does affect that when they're occurring in time, and also when they're spatially where they're occurring. And so one of the silver linings of this type of work is that we're beginning to understand this link, looking at the Earth as a coupled system and thinking about how changes in climate can affect what's happening at the Earth's surface, and then how that can affect processes that are happening deeper in the Earth, so earthquakes. And if we better understand that, then we can monitor and track these changes and be able to identify regions and time periods when the hazards might be more elevated, so that people are aware and at least prepared for earthquakes, whether they're small ones that are just causing a little bit of shaking, or the possibility that we may have a larger one that could damage property and impact lives.
Right. Well, I think that brings us to the end of today's programme. But Sean and Verena, thank you so much for joining us on the climate question today. I really learned so much.
Thanks, guys.
Thank you very much for having me.
Thank you both for having me.
And thank you for watching. Don't forget to subscribe to the BBC World Service YouTube channel so you don't miss a thing.
And if you have a climate question of your own, then do comment it below and we'll answer it in a future show. I'm Greg Jackson.
And I'm Jordan Dunbar. See you next time.